Hello, welcome to section 2.3, characterizations of invertible matrices. This is the final section we will cover in chapter 2, and you'll find that it's a review of the chapter 1 concepts. So basically, n linear equations with n unknowns in relation to square matrices. So we're really going to be focusing on square matrices and characteristics of whether or not they are invertible. Now, when you are doing the homework, you're going to have to dig deep and remember a lot of those concepts that we have learned previously. So we're going to start off with just a theorem. And the theorem is stated here. And as you can see, there are several parts to this theorem. But a few things that I want to remind you. An invertible matrix, remember, is a square matrix that has an inverse. Well, all of these statements are equivalent. Now, again, it's important to mention that it's a square matrix. And all of these things, there's a lot, but of course, in this course, you do not have to memorize these things. But either all of these items listed here are true, or all of these items listed here are false. I think that it would be helpful for you to pause the video and take a moment to read through these and, just kind of become familiar that they are a part of this theorem. Okay. Now, one thing that is not part of this theorem, but it's something that we saw in the previous section, you'll see this in your homework also. If the determinant, so if you have a 2 by 2 matrix, for example, and the determinant does not equal 0, then the matrix is invertible. And you'll want to remember that for your homework over this section. So a little bit more about all of the statements on the previous slide. Basically, if statement A holds true, then that implies statement J. And I believe you have seen this notation in your previous courses, but this just means A implies J. Now, this proof is very circular. You will find that if any of these 5 statements are true here, any of those 5 are true, then the others are true as well, because it's circular. A implies J, J implies D, so on and so forth. So it's like a circular set of implications here. A few other things. Theorem 8 could be written as the equation ax equals b has a unique solution b in Rn. Just pause this and read through this. I don't think it's necessary that I read all of this. This one is important, however, if A and B are square matrices, if A times B is the identity matrix, then both A and B are invertible. So that means B is equal to A inverse and A is equal to B inverse. Okay, so, it should make logical sense, but I don't know. The invertible matrix theorem basically divides items into 2 cases. It is either invertible or non-invertible. You'll find in this section that it's really review, so I don't have a lot of examples. just a lot of reminding you of different things. So again, it's very, very important that you notice that all of the properties that were stated in that theorem pertain to square matrices. You can read through this. Okay, so let's look at the types of problems that you'll see in your homework. So here's one type. It will say, determine if matrix A is invertible without actually finding the inverse. Now, in the previous section, section 3.2, I'm sorry, 2.2, we talked about finding the inverses. Now, in this section, we're not finding those inverses. Now, what we're trying to do is to just be able to use that theorem that was shown to you initially and decide if the matrix is invertible or not. So basically, if it's a 2 by 2 matrix, find the determinant. If the determinant equals 0, then it's not invertible. Done. Okay, but if it's a 3 by 3 matrix, like in this example, it's a little more complicated. So what I would recommend doing is begin by row reducing. So if you row reduce A, it becomes along the way this. And you can check this work if you want, or you can just trust me. I feel like at this point in this class, I think that we have a pretty good relationship, and trust should hold. So here, you'll notice that we have a row of zeros. And in this case, if you look at this, there are only 2 pivot positions. And if you refer back to that theorem at the beginning of the section, it says that A, so if we have an n by n matrix, then A has to have n pivots. Well, in our case, we have a 3 by 3 matrix, so we need to have 3 pivot columns. And we only have 2. So this matrix is not invertible. Okay? Because this matrix is not invertible, all of the other statements in the invertible matrix theorem are not true for matrix A, because it's all or nothing. They're either all true or they're all false. Let's look at this example. Same rules apply. Let's row reduce. If I'm trying to row reduce this, the first thing I'm going to want to do is try to get those to be 0. So this becomes 1, 0, negative 2, 0, 1, 4, 0, negative 1, negative 1. If I proceed, if I add row 2 to row 3 and get a new row 3, I get the following. And if you look at this, there are 3 pivots in this 3 by 3 matrix. So there needs to be n pivots in the n by n matrix. Therefore, this is true, so A is invertible by the invertible matrix theorem. Sometimes the invertible matrix theorem is shortened to IMT. So I think I've emphasized this enough. So if you're dealing with a 4 by 3 matrix, then we cannot use the invertible matrix theorem to draw any conclusions. So matrix multiplication corresponds to composition of linear transformations. So basically, and we kind of discussed this before, but A inverse times AX equals X because these are multiplicative inverses. So it's just kind of shown here what happens. If you take X times A, you get AX. And if you take AX times A inverse, you get back to X. So again, it's a bit circular. The last thing I want to talk about here is Theorem 9. It basically wraps up everything that we've talked about. Just kind of talking more about that circular pattern that we saw in the previous section. If you have something like this, then T of X is really the inverse of S, since you get back to X, and S of X is the inverse of T. And this is all just shown here. So they are invertible. And I was trying to break the goal of having the shortest video yet, and I achieved that. You're welcome.